The Helios rocket is a proof of concept for a class of water bottle rockets that can carry payloads to moderate heights. The first rocket planned to use this method is the Icarus rocket, which will be able to carry small payloads to deploy at apogee. The deployment chamber could also easily be retrofitted to hold a small camera or other such instruments. After comparing different brands of water bottles, Smart Water was chosen because of the minimalist form factor of the bottle. The flat walls also make it possible to mount sections to each other without an inner stage, simplifying the design considerably. Before being assembled onto the flight hardware, all of the software for Helios was tested on a full-size Arduino and breadboard so that changes could quickly and easily be made to the design. A cardboard sled was chosen to act as the capsule's internal structure. This design is lightweight, provides simple compartmentalization, and can take a beating without failing to hold all the electronics in place. The cardboard material also makes it very easy to attach parts with its simple wire ties, which can be twisted down to tightly grip the structure. The software for Helios runs on an Arduino Pro Mini, which only contains the essential parts of the Arduino in order to maintain a small form factor. The software is loaded into the Arduino with a programmer chip that is connected to the Arduino through a 6-pin interface. A toggle switch on the board switches between internal and external power mode. In external power mode, data can be read off the chip with a serial connection into a text file that can then be further analyzed. The top compartment of Helios contains the battery. In addition to providing power to the rocket, this compartment acts as a crumple zone, absorbing the kinetic energy of a hard landing so that it doesn't damage the rest of the rocket. The white cap is particularly adept at this, oftentimes inverting itself on impact, absorbing almost all energy from a hard landing. A version of the rocket with an empty capsule was also made so that kinetic tests could be performed without risking the flight hardware. During these tests, the top compartment is filled with enough water to mimic the weight of the components that go into the actual rocket. Before testing the rocket with flight hardware, tests needed to be performed with the mock rocket to make sure that the parachute would be deployed in time and slow the rocket down sufficiently as to prevent it from sustaining damage. These tests led to a lighter plastic parachute design that used talcum powder to prevent the sheets of plastic from sticking to one another. The original design called for fins on the rocket motor, but testing showed that the whole rocket motor acted as a fin. This was because the relatively heavy capsule pulled the center of mass of the rocket forwards past the center of drag. On discovery of this, the fins were removed from the design. The method of barometric pressure sampling proved to be unreliable because of the shifting atmospheric pressure from the weather. A promising alternative to this system is the idea of detecting the apogee based on the orientation of the rocket. Because the rocket tends towards facing in the same direction as its velocity vector, we can assume that any time the rocket is pointed downwards, it is descending, and thus should have the parachutes deployed.